Hi everyone, my name is Paloma Sodi and today I'll be presenting our work LEO, Learning Energy-Based Models in Factor Graph Optimization. Consider this problem of a robot arm pushing around an object. We are interested in localizing these object poses from touch observations or measurements. That is, at each time step, we receive a sequence of tactile image measurements from which we must infer a sequence of latent object poses. A common way to solve this is as an inference problem over a factor graph which relies on having observation models that can map between observations and states. However, image-based tactile sensors such as these produce observations that are complex and typically difficult to model. Can we instead learn these observation models from data? What would this learning look like? So, in the forward pass, we have a learned observation models feeding into the graph optimizer to produce an optimized trajectory x hat. This is then compared to a ground truth trajectory xgt to compute an end-to-end tracking loss L theta. The loss is then backpropagated through the inference step to update theta. But there are two main problems with this approach. The first problem is that many state-of-the-art graph optimizers are not differentiable. For instance, the ISM2 graph optimizer, used popularly for SLAM, invokes a series of non-differentiable Bayes tree operations and heuristics. A second problem is that even if one did want to differentiate through the nonlinear optimizer, one would typically have to do this by unrolling through successive optimization steps and then propagating back gradients through the optimization procedure. However, training in this manner can have undesired effects. For example, prior work has shown instances where even though unrolling gradient descent drives training loss to zero, the resulting energy surface does not have a minima on the ground truth. In other words, the learned energy surface is sensitive to the optimization procedure used during training. For example, the number of unrolling steps or even the learning rate. We argue that instead of caring about the optimization procedure, we should only care about the shape of the function that the optimizer has to minimize. This is precisely what energy-based models aim to do. In this paper, we propose an approach LEO, learning energy-based models in factor graph optimization. Let's start with the ground truth trajectory xgt. To easily visualize the energy function, we will collapse the trajectory down to a single axis. Now let's initialize with a random energy function. Note that the ground truth xgt is far from the minima. LEO begins by sampling trajectories x hat around the minima by invoking the graph optimizer. The energy-based update rule is simple. Push down the cost of ground truth trajectories and push up samples around the minima. If we keep repeating this process, the minima of this function eventually centers around the ground truth. At convergence, the gradients of the samples x hat on average match the gradients of the ground truth trajectory xgt. So how does LEO work in practice? Let's begin with a simple 2D problem. We have samples from a ground truth function and we would like to learn a network that maps a point xy to an energy value. We randomly initialize the network visualized here with high energy values in dark blue and low energy values in white. Notice that the ground truth is quite far away from the minima. Over successive LEO iterations, the energy value converges to a basin around the ground truth function, shown in green. So we repeat this experiment with varying seeds and samples and observe that LEO consistently converges to an energy function with low energies at ground truth and high energies elsewhere. Now let's look at some robot applications. The first is a synthetic navigation task where the goal is to estimate robot poses from orometry and GPS observations. The second is a real-world planar pushing task where the goal is to estimate object poses from tactile image observations. For synthetic navigation, we learned covariance parameters for GPS and odometry measurements. These are results on some of the test data trajectories. We initialize LEO with random covariance parameters, and over successive iterations, as you can see, it is able to learn parameters that drive optimized trajectories close to ground truth. Here we focus on one such trajectory and visualize how LEO samples evolve over iterations. Initially, when the energy function is incorrect, samples are more spread out. Over iterations, as the energy function evolves, the samples concentrate about the ground truth. For real-world planar pushing, we learn both mean and covariance parameters for tactile image measurements. This is a typical planar pushing trial with a rectangular object. The top left shows the tactile images captured by the digit tactile sensor. As the object is pushed, we see that the contact patch in the tactile image observations move around based on rotations about the point of contact. We evaluate LEO on test data trajectories with two different objects, a rectangle and an ellipse. We initialize LEO with random model parameters, and over successive iterations, it is able to learn parameters that drive optimized trajectories close to the ground truth. For more details, please check out our paper. Thank you for your time.